Hi everyone, Civil Engineering 331, Hydraulic Engineering here for the 23rd of January 2013. It's a Wednesday, class number 4 for the semester. I'm going to be heading to Washington, D.C. for a conference, and so you're going to be having this lecture online. Just to look at a couple of announcements, remember that today's class is online. Also Friday is going to be. On Monday we're going to have a brief quiz in class at the beginning of class in order to assess whether you were able to view the lecture. Homework number 1 is due on the 25th. That's Friday while I'm gone. Slide the assignment under my office door so that I can collect it over the weekend, and then the quiz that we have on Monday will include some coverage of the concepts that are in that homework assignment. If you've got questions about these announcements, then please feel free and send me an email. I'm going to be doing my best to check my email while I'm away, and then again over the weekend. wait@marshall.edu. Well, let's go ahead and get right into the material. The bulk of today's lecture is actually pencast examples and screen recordings, but we'll talk about some of the fundamentals before we get into those examples. Here it is. This is the Colebrook equation. You know, I've been hinting starting in fluid mechanics that there's this really hard way to find the F value. You know, I'd give you the F value in an example and say, you know, really, in a real problem, you're not just given the F value outright. Well, here it is. This is what I was hinting at that whole time. It's the full-fledged way to calculate the roughness F value that we have to insert into the Darcy-Weisbach equation in order to find head loss due to pipe friction. This Colebrook equation, as it's known as, is valid anytime the flow conditions aren't in the laminar range. When the Reynolds number is below 2,000, then it's easy for us to find the F value because the F is just 64 divided by the Reynolds number. Otherwise, Colebrook equation is valid. The Colebrook equation, the reason why it's a little tricky to solve is because it's an implicit equation. The F value is on both the left-hand side and the right-hand side of the equation. And besides that, it's actually buried in the denominator in a square root, so that no amount of algebraic manipulation is going to get that F value so that it's just in one spot. It's an implicit equation. So solving it means that you're going to have to pick some guess value of F, see what the left-hand side of the equation is equal to, see what the right-hand side of the equation is equal to, and if your guess of F was correct, then those two sides will be equal, and that will let you know you've got the correct F value for the flow conditions that are described. Here are some relative roughnesses, and we've seen tables like this previously. In our text, the variable epsilon is assigned to relative roughness, but the rougher materials like cast iron or concrete has an equivalent sand roughness in the range of 0.26 up to 3 millimeters. Glass and smooth tubing may have a relative roughness that's much lower. What I want you to notice about the structure of the Colebrook equation is what's inside this log term. Inside the log term there are two components. There's this k sub s divided by 3.7d. So remember in the Moody diagram that there is a portion of an F value curve that's curved and a portion of it where it's flat. Well, the k sub s divided by d, that is sort of the dominant thing that determines the F value when the Reynolds number is high. Reynolds number is on this other term, and you'll notice it's in the denominator. So that if you've got a really big Reynolds number, you know, as that gets big down in the denominator, then that whole term of 2.51 divided by the Reynolds number to multiply by the square root of F, this whole term becomes insignificant with the big Reynolds number. When the Reynolds number is relatively small, then it's not to be neglected. But that's just to give you an idea of how it behaves, and we'll get a better sense for that in an example. So here in this example, we've got water flowing through a 136 millimeter diameter pipe made out of galvanized iron. We know the K sub s from that galvanized iron pipe by looking it up in a table. Flow rate of 200 liters per second of water, and the kinematic viscosity for water is provided at 20 degrees Celsius of 1 times 10 to the minus 6th. So we're going to solve this using the trial and error approach of just by hand calculating the left-hand side, the right-hand side with some guess value of f, and then stopping when the two sides are equal. And we're going to apply that method also using Microsoft Excel. Okay, well, that concludes today's lecture. We've been through the hand calculations, we've been through the example showing how to do the trial and error, how to type in the Colebrook equation in Excel, and I really would encourage you to get practice typing that equation in. And also you got to see what goal seek looks like, so it was a good day. Looking at these announcements, remember that there's going to be another lecture posted for the Friday class. That's going to be online as well, and please get that homework into my office by close of business on Friday. Hope you have a great day, and I will talk to you later. Bye. This example is showing how to use the Colebrook equation. And in this example, we're going to be looking at flow through a pipe where the diameter is 136 millimeters. And the K sub S, which is the equivalent sand roughness of that pipe, is 0.15 millimeters. The flow rate that we're given is 200 liters per second. And essentially what we'd like to find here is what F value would be used in the Darcy-Weisbach equation of H sub F is FLV squared over D2G. So we're going to try and find what would be the friction factor under the conditions that are described so that we could then calculate the head loss through the pipe. The F that we calculated in fluid mechanics were sometimes just given to us directly. This Colebrook equation is really the meaty, real way to do it. And we're going to take a look at, by hand, what the trial and error approach looks like. So the Colebrook equation is shown there. Of course, the Colebrook equation is an implicit equation, meaning that the unknown we're trying to solve for is on both sides of the equation, and no matter what algebraic manipulation we do, it's going to stay on both sides of the equation. So our approach will be to guess some value for F, and then try and get our guess to be better and better over time. Let's look at some preliminary stuff here. The diameter of 136 millimeters, we've already specified that. The flow rate, that is 0.2 cubic meters per second if we convert from the liters to cubic meters. The Reynolds number, of course, is velocity times diameter divided by kinematic viscosity. And we want to find the velocity through the pipe. It's Q divided by A. The area of the pipe here is going to be D pi d squared divided by 4. So pi 0.136 meters squared divided by 4. That gives us an area of 0.01453 meters squared. And so then the velocity will be the flow rate, 0.2 cubic meters per second, divided by 0.01453 meters squared. The velocity is 13.77 meters per second. The water is moving along in that pipe. So we'll put that into the Reynolds number, and 13.77 meters per second times the diameter of the pipe, 136 meters, divided by the kinematic viscosity of water. Here we're told on screen that the kinematic viscosity of water is 1 times 10 to the minus 6th meters squared per second at standard 20 degrees Celsius. So 1 times 10 to the minus 6th meters squared per second. The Reynolds number that we'll end up with, 1.8 million. So we're going to substitute that Reynolds number along with everything else that we know into the Colebrook equation. And so the right-hand side of the equation is going to be 1 divided by the square root of f. The left-hand side of the equation is going to be
negative 2 log k sub s 0.15 millimeters divided by 3.7 times d in millimeters, so that we can be consistent with the k sub s units of length, plus 2.51 times the Reynolds number, 1.872 times 10 to the 6th, square root of f. Alright, so we're going to take a guess value of f and see what is the left-hand side and what is the right-hand side. Let's say, for example, what if f is 0.02? Well, we'll get all our calculators out. And you're not just watching this pencast, you're doing the calculators stuff and following along, because it's irresistible when you're an engineer to do calculations. So 0.02 square root 1 over 0.07. Oh, I'm sorry. Yeah, it's not scientific notation there. 7.071. Okay. What about the right-hand side? So when we do our substitutions, I'll write it in this first time. Negative 2 log. So there's going to be, this isn't going to change as we substitute in lots of different values for f. So 0.15, 3.7, 136 times divided by 2.981 times 10 to the minus 4th is that expression, plus 2.51 divided by 1.872 times 10 to the 6th. This term is 1.341 times 10 to the minus 6th divided by the square root of f. Okay, so in this case, remember what I'm substituting is let f equal 0.02. So what is that entire term when we make that substitution? 0.02, square root of that divided by plus log 2 negative times 7.024. Boy, we're already pretty close, it looks like. They're not exactly equal. If they were equal, then that would tell us that we had the correct value for f. So we're not there yet. Let's just say, by the way, the range of possible values for f uh, 0.008 all the way to 0.038. Those are sort of the likely ranges of f that we're going to see. So knowing that range gives you an idea of, where to start. I just sort of picked the middle value here. Let's take a look at how does the right-hand side and the left-hand side respond if we instead substitute in let f equal 0.01. We'll go through the calculations. We find that the right-hand... I do know my right and my left. There we go. That makes more sense now, doesn't it? Alright. And I'm going to post this even though it's got an error in it, just so that you know it's okay to make mistakes. Alright, so the f value there of 0.01, the left-hand side is equal to 10, right-hand side 7.013. So, boy, that seems like we're worse than it was before. And so maybe we'd want to try some other value. We could substitute in the f equals 0.022 and see if that's a little bit better. And so if we go through that process of trial and error, eventually what we'd find is that the f is 0.0203 if we repeated it over and over, making tiny incremental changes to f. How do you know when to stop? Well, we usually only use f F values to 3 digits of accuracy. And so you can see that this extra one here is sort of going a little bit further than we'd need to be able to actually define it. So we'll transition to taking a look on how to do this on computer next, but that's essentially how you solve Colebrook by hand.
Okay, well, let's go ahead and try out the Colebrook equation using the trial and error approach, but with the aid of a computer to simplify our calculations. It's the same process that was illustrated in the pencast example, but this time we're going to be able to just repeat guess values of f really quickly. Remember that our first guess value of f was 0.01 in that paper example, but just to illustrate the range of possible values, we'll start at the low end here of f, and we'll do it in increments like that. Okay, so the left-hand side of the equation, yes, I do know my left, the equation there is 1 divided by square root of whatever f value we're guessing. Okay, now the right-hand side will be a little bit trickier to write out the expression for that. So it is -2 times log of our k sub s value, remembering to anchor that because I'm going to be, oh, okay, I've actually named that cell k sub s, it looks like. I don't know if you've, let me just show you that trick really quickly. You can name a cell, you know, like this cell, for example, has a name of C8, and so you can see it's named C8, and so anytime I want to refer to it, then I'll just type C8 in an equation, or if I wanted to refer to this cell, I'd type in A2. Well, you can rename what you call something just by typing in here. Like if I wanted to call that cell, you know, variable 1, well, maybe it didn't like the fact that I had that dash in there. Variable 1. So now, anytime in a formula, if I type the word variable 1, it would be referring to that cell. Well, why does it matter? Because I previously had named this cell, instead of calling it B3, I'm calling it K sub S. I'm calling that D. And I'm calling that Reynolds number. That maybe will make it a little bit easier to construct our equation, to know what is what. So, -2 times the log value of K sub S divided by 3.7 divided by D. That's a little trick if you don't want to put in lots of parentheses. You could write this equation K sub S divided by 3.7 times D parenthesis like that, or you can do the double divide, divided by 3.7 divided by D. That's numerically the same thing. It'll save you some keystrokes if you get used to it. Plus 2.51 divided by Reynolds number divided by the, now I am going to have to put in, I think, an extra parentheses there, divided by square root of our guess value for f, which was A10. Okay. 7.01. So of course the beauty of setting it up like this is that I change my value of guess value of f, and when I drag the formula down, it automatically calculates the new value. So we'll go over the entire range of possibilities. About 0.38 is as high as we'll ever get with an f value, and drag all those down by double clicking. And this difference column here will help me to know which solution is closest. So I'm just going to do one minus the other, and I'm going to try and find the smallest difference possible. So where is it? It looks like my smallest difference is right there. And so the two aren't exactly equal, which means I need to, the solution is a little bit greater than 0.02, but a little bit smaller than 0.021. So I could, you know, put in other values, 0.0201. That got better, and I'll be able to show it there, 0.02. That improved even more. What if I said 0.03? Oh, that looks really great. So what if I do 0.04? Got worse. So that is my final answer there. So that's the trial and error approach. We can use goal-seek to find it as well. Goal-seek is a tool that's built into Excel that I think maybe you've had a chance to use before, but let me just refresh your memory on how it can be useful. We're going to do the same thing as before. Here on this cell, I've got, it's called K sub S. I must be illustrating goal-seek with some other problem. I'm going to do it with this one anyway, because I'm so excited to show you goal-seek. So I'm going to copy this. Alright. So check this out. Delete all of these. So I start off with some guess value, 0.008. My left-hand side, 1 divided by square root of f. And I hope you're doing this. I hope that you're at a computer watching this, or maybe you're watching this on a tablet, but then right next to the tablet you've got Excel running so that you can get, get your hands dirty with the equations, get some practice with this. It's not much to watch if you're not also doing it. If you're doing it at the same time as you're watching it, then you're having a ball. But if you're just watching someone else do Excel, boring, because you're wishing that you were running Excel, of course. So -2 times log of K sub S divided by 3.7 divided by D plus 2.51 divided by Reynolds number divided by square root of f. Too many parentheses. Yep, that's fine. Alright. Difference, of course, is that minus that. Well, what's our goal here? We want to have a really small difference. So with goal-seek, what we're going to tell Excel is, don't make me drag that cell down. That's exhausting. And I know that you can do that just as easily as I can. That's what we're going to tell Excel. So the way we tell it is with data, what if analysis, goal-seek. What if you did it for me, Excel? So what we want, our goal is, we seek for the difference to be 0. And what should it change to do that? Well, play around with the f value. Keep changing the f until the difference is 0. And Excel will do it, okay? And it finds the value. Alright. A little strange, though, that it wasn't exactly the same solution that we found. We found 0.0203. I wonder if it's an error in the way I wrote that formula, if I should have put in another parenthesis somewhere. Order of operations thing. 2 log times. Well, let me just do one more thing, because there's an even more powerful tool besides the what-if analysis goal-seek. It's solver. And what we want is our difference to be 0 by changing f. So go ahead and solve now. Oh, I found the same one. Okay. Seems strange to me that it didn't find the exact same solution. I wonder if I've got a... Oh, let's see an error in my solution here. Now I think it'll be good. Let's do goal-seek. We want the difference to be 0 by changing f. And that's what I'm talking about. Now it's equal. You know, you get in a hurry and you miss a parentheses in Excel, and you're going to get bad results. Now, why was it not worse than that? Why was the mistake not really that relevant. Well, of course, the Colebrook equation has two parts. It's got this part here has to do with the relative roughness. And this part of the equation has to do with the flow conditions. And remember where we're talking about fully turbulent flow versus smooth pipes. Well, when you get above a certain Reynolds number, it doesn't really matter much. This term becomes irrelevant. If you look, the Reynolds number is in the denominator, so a really big Reynolds number, and this term isn't going to matter. So the mistake I was making when I typed in when that extra parentheses wasn't there, it was only taking the log of the first expression. It wasn't considering that other expression. Well, it just so happens that it's only this expression that matters very much with a really high Reynolds number. If the Reynolds number had been a little bit lower, then it is important both terms are relevant. But with a high Reynolds number, this term moves towards 0, and then the F value is really only a function of the relative roughness. So I guess we all learned a lesson today. That concludes the trial and error method, where you're typing in the equation and dragging down the F values, and then also you gotta see how goal-seek works and even a sneak peek at Solver. So please let me know if you've got any questions.